Hello everyone, this is a video tutorial of problem B box fitting of CodeCraft 2021. So before diving into the solution, we will first look at the problem statement. So you are given n rectangles and each rectangle is of height 1 and each rectangle's width is a power of 2. We are also given a two-dimensional box of width capital W and it is given that the width may not be of power of 2 and it is also given that the width of the box will be at least as large as the width of the largest rectangle. Now our task is to find the smallest height of this box such that it can fit all the given rectangles, all the n rectangles, and it is also allowed to have some empty space left in the box after we fill all the rectangles. Also, we cannot rotate these given rectangles in any form other than what it is given, and we cannot have any rectangles that have a positive intersection area, so they must not overlap. So we will look at an example after we discuss input. So looking at the input, in the input we are given t number of test cases, where in each test we are given two integers n and w, where n represents the number of rectangle and w represents the width of the box. And in the second line of the test case we are also given n space separated integers wi, so they represent the widths of n rectangles. It is also given that the width of the box is greater than, at least as large as the width of the largest rectangle. And it is also given that sum of n over all test cases will not exceed 10 to the power 5. For output, for each test case you have to output a single integer that will contain the smallest height of the box that can fit all the rectangles. So let's look at a sample input. So we are given one test case and we have 5 rectangles, and the rectangles widths are 1, 2, 8, 4 and 8, and the width of the box given to us is 16. So in the optimal condition there can be multiple output configurations, but the height will remain the same. So one of the possible optimal solution is putting boxes of 8 stacked each other for height 2 and then keeping the remaining rectangles of width 4, 2 and 1 on the first layer. So there are sums up to 15, which is less than 16, so it is allowed, and we get a height of 2. We cannot achieve height of 1 in any case, so this is the optimal answer. Now let's dive into the solution. So we'll first talk about the greedy strategy. What the greedy strategy is, we'll prove later that it works. So what our strategy is, in the current layer pick the largest available rectangle that can fit into the current layer, that whose rectangle's width is less than the space that is left in that layer. We place it there and keep doing it until we cannot do it. So repeat until possible. And if we cannot place more rectangles in that layer and we still have some rectangles to fill, then we add a new layer and start doing the first step. So we first then again pick the largest rectangle that can fit into the new layer and then keep doing it until we have no more rectangles left. So this is the strategy, this is the solution, but we don't know why it works, so we will prove it. So before proving it, so brief proof, intuitive proof is that it is always possible to replace several smaller blocks with a single larger block if it is available. And since all blocks are power of 2, so it must happen that the smaller powers of 2 will sum to a larger power, and therefore we can replace those smaller powers of 2 rectangles with the rectangle having the larger power of 2. So this is not an elaborate proof, and this is just a brief intuitive proof which is sufficient for you to solve the problem, but we will dive into the mathematical details of the proof now. So this is a more sophisticated proof, we will look into it. So let's first look at a property. So if it is the case that some widths which are power of 2, w1, w2, wn, they are sum up to a greater than w0, then there must exist an I such that sum of first of I widths will sum up to w0, and they are non-increasing, so they are decreasing, but equality is also allowed. So can you prove this? Why does this property correct? So we can take an example and observe this property intuitively. Suppose we have something such as widths are 4, 2, 2, 1 and 1, and we have w0 equal to 8. We know that 4 plus 2 plus 2 plus 1 plus 1 equal to 10, which is greater than 8. But we can always take 4 to 2 and that sums up to 8. So a prefix of these elements will sum up to 8, and this is a standard property. If the elements are power of 2, you should try looking it in the web so to prove it. Now going into the mathematical proof, so we will we'll give a proof by contradiction. So let's say there is an optimal solution that gives a height lesser than our greedy solution. So what we will do is we will look at the first point of difference. So if we start from the left and if we start from the bottom, we check the configuration of our greedy strategy and of the optimal strategy, and we will look at the first point of difference. So looking at the first point of difference, so let's say that the widths of the optimal rectangle that is placed is BO, and the width of the greedy strategy that we follow is BG. So there might be three cases. So in first case, the height or width of the optimal might be greater than the width of the greedy, but this is never possible since in our greedy we choose the largest width rectangle that can fit into the current layer. So this is never possible. The second case can be the optimal has the same width as the greedy, but that is not the difference. We want to look at the first point of difference. So this is also not relevant for us. The only thing that will be relevant for us is when the optimal is less than the greedy. Width of the optimal rectangle is less than the greedy rectangle at that point of difference. So now we have to prove that both will give the same answer. So let's say that the optimal solution will place several consecutive smaller blocks and not just one block. So, and we also assume that we also rearrange the optimal rectangles in decreasing order. That will not make a difference in the order, it will just help us in the proof. So since the blocks are in non-increasing order, none of them would be greater than BG, because otherwise it would have been there. So now only two cases are possible. Two cases for case 3. The two cases are that the sum of those all the blocks, smaller blocks, sum is either less than BG. In that case, our solution will be better because we are putting a larger sum. So it is not relevant for us. What if sum is greater than equal to BG? Then what we can do is we just proved a property above that the prefix of this sum will always equal to BG. So we can select those prefix first I elements of the sum such that they sum up to BG, and then we remove those first I rectangles, we replace those rectangles with the same width BG, and we will get the same sum. So we swap them. So we show that any optimal solution can be rearranged in such layer that those layer will always put the first largest rectangle width of rectangle that is available, and that is what is our greedy strategy is. So therefore after we rearrange, we prove that our greedy strategy gives the same answer as that the optimal. Now we'll walk through the code. So we first scan the number of test cases. Then for each test case, we take the number of rectangles and we also take the input of the box width. And so what we will do is, to code it, first we'll look at how to code it. So what we'll do is store a frequency array where we store the powers of two rectangles that are there. So for each w that we take, this is the width of the rectangle, we store it what is that power. So log 2 w will give the power that is exponented to 2, and we will store that in a count array. So counts I will contain the number of rectangles that have width 2 to the power I, and it will be always less than 2 to the power 20, since we have only the width can always be less than 10 to the power 6. So the log 2 of that 10 to the power 6 will always be less than 20. So size 20 is sufficient. So now in the counts array we have the counts I will give the number of rectangles that have width 2 to the power I. And now according to our greedy strategy, so we will keep on selecting the largest rectangle that we can fit there. So we run n iterations for putting n boxes, n rectangles, and we initialize the largest to -1. Now we iterate through the counts array and see if those exist. So count size, if it exists and the size of that rectangle is less than the size space left in that, we can put it. So we will put it and break. If there does not exist any such rectangle that we can fit into the current layer, then we initialize increase our height of the box by 1, and the space remaining will now be the box width. So since we can again put it, and then we will again do the same thing. So we will scan through the counts array and check if any rectangle fits, and we will take the largest such, and we will decrease the frequency of that rectangle width, because we already took one, and the space left will be space left that was there before, and then we will subtract the width of the rectangle that we put. We had initialized the height to 1, and now we keep on increasing height until all rectangles are over, and that will be our final height. So that was just one greedy strategy. We could have thought of numerous greedy strategies. Let's look at some of them. So one of the greedy strategies would be to sort all the rectangles in decreasing order and then keep putting it until there is space remaining. If there is no space remaining, then we will increase the height by 1 and then keep on doing it. So the strategy would be sort in descending order and then keep putting the boxes. Another strategy similarly will be to keep the boxes in rectangle in ascending order. And one third greedy strategy would be to sum up all the W's, the widths of the rectangles, and then divide by the width of the box. So we will do sum up all the rectangles, widths of the rectangles, and then divide by the width of the box. And we also have to take the ceiling of it, because otherwise if there is one remaining, then we would have to increase the height by 1. That's why we have to take ceiling. So if it does not divide it perfectly, then height would be 1 more than the answer that we will get by integer division. So let's look at why they will fail, why only our strategy will work and these strategies will fail. So let's look at a counter case. So a counter case would be, there might be 12 rectangles and the width of the box will be 11, and the widths of the rectangles are 8, 8, 8, 1, 1, 1, 1, 1, 1, 1, 1, 1. What our optimal strategy will, optimal greedy strategy, what our optimal greedy strategy would do is, we will take first 8, then we have only 3 space remaining, so we cannot fit 8, so we'll put 3 ones. Then no space is remaining, so we get to a new height, we put 8 there. Similarly we put 3 ones here, and then we again put 8, and then we put 3 ones here. So we will get height of 3. Now what will be the descending order strategy? So we'll first sort in decreasing order. We will get 8, 8, 8, and then 9 ones. Now we'll try to first put 8. We'll put 8. Now we'll try to put second 8, but we don't have enough space, so we initialize a new layer. So we get another 8. Now here also we don't have space, so we initialize another layer. We get 8. Now since there is no space left, we go to a new layer, and then we'll put all the 9 ones here. So we get height of 4, which is suboptimal. Now what will the ascending strategy do? Similarly, it will do the very similar thing. It will first put all the 9 ones in one layer, and then it will have to put 8, 8 and 8 in subsequent new layers. So we will also get a height of 4, which is also suboptimal. Now let's look at the seal solution. So seal of sigma w upon capital W. So that will give us 8 plus 8 plus 8 plus 9 ones, that is 33, and the width of the box was 11. So seal will give the same answer, we get 3. So this seal works on this test case. But suppose there is another test case where number of rectangles is 9 and the width of the box is 9, and we have 9 rectangles of width 8. So now what our optimal solution, greedy solution, will do is put 1 8 in each of the layers, so we get a height of 9. So the best optimal answer is 9. Now let's see what happens in the seal solution. We will get sum will be 72 and we divide by 9 capital W, that will give us 8. After taking the sealing, it's still the same, we get 8. So this gives a better answer, but that is wrong. So the seal solution also fails. So our optimal greedy solution works. Now you would ask, what if those widths that were given are not a power of 2? Why wouldn't our solution work? Well, it won't work. Suppose, let's say we have 6 rectangles and the width of the box is 13. Now we have width of the box is 13 and the widths of the rectangles are not power of 2. Say suppose 6, 6, 4, 4, 3, 3. Now what our optimal strategy will do is we will first place 6, 6, then 4, 4, 3 and then 3. So we will get height equal to 3. But there exists a better solution, that is 6, 4, 3, 6, 4, 3. So which is of height 2. So there is a better solution, but our greedy will fail and give a suboptimal answer. So that's why their power of 2 was a must to prove our greedy solution. Otherwise the prefix of 4, 3 can never be fulfilled by 6. So that was our argument, that if sum is greater than what we put, then there must exist a prefix of that will sum up to this 6. So but a prefix of 4, 3 does not sum up to 6, and hence our proof doesn't work and our greedy solution fails. Now as an exercise for the viewer, you are left to prove that if the width of the box was also a power of 2, then all those greedy strategies we discussed, the descending order sort, ascending order sort, and the seal sigma by capital W strategy, they will all work if the width of the box was a power of 2. That proof is left as an exercise to the viewer. So well, that's the end of the editorial. Do like, share and subscribe to our channel, and also we have editorials of other problems. There are also lots of other educational content out there in our channel, so please check that out too.